In a solution, you have to remember that there actually are different kinds of solutions. Now, most of the time, what we're going to talk about are homogeneous solutions. And what happens in a homogeneous solution is that you have two different substances and they combine into a single phase. So in the picture in the middle lower part there, probably that's a copper 2 chloride compound. On the right, it's kind of a blue solid. Looks kind of cool, actually. But anyway, when you dissolve it in water, then you make that blue solution, which is what you see in the beaker. And the blue solution has like a stirring rod inside. You want to make sure the solute is totally dissolved. That's an example of a homogeneous solution. Everything comes together. You had a solid, the copper 2 chloride, and water, a liquid. And at the end, the solution looks like a liquid, all right? It's not really a liquid, but it looks like a liquid, all right? That's a homogeneous mixture. You can have a heterogeneous mixture, which is if you'd put, for example, like a rock in water. Most rocks don't dissolve in water, so you can see the rock, a solid, in the water, a liquid, two different phases. So we're going to talk in this section just about homogeneous mixtures. Now, solutions are great examples of what chemists can really do, and that's what we're going to focus on. But depending on actually what happens in the solute, you can also make a colloid or a suspension. So we'll talk about those briefly, but in the back of your mind, just realize most of what we're going to do is talk about these solutions, all right? Solutions are really cool. We encounter them all the time, all right? Solutions are all around. Coffee is my favorite example. Woohoo! I love my coffee, but that's a personal problem you don't need to worry about. There are actually, though, other kinds of solutions that are pretty common to us. So, for example, the air you're breathing right now is actually a solution. You've got oxygen mixed in with a lot of nitrogen to make an air solution, a gas solution, which is kind of cool. And the ocean is definitely a solution as well. All kinds of stuff dissolved in the water, for better or worse sometimes. But anyway, this is the kind of material that we'll be covering in this section. A solution has a solute and a solvent. And the solute is the substance that's being dissolved, quote unquote, and the solvent is the substance that's dissolving the solute. I don't really like either one of those definitions. It's hard to define solute and solvent. But here's the thing, all right? If you take sugar, like in the example there, the next one, and there's different types of sugar, but this sugar is C12H22O11. And sugar is a solid, if you've ever used it, white solid, kind of cool. It dissolves really well in water to make a sugar solution. So on the right-hand side of the arrow there, that C12H22O11AQ, that's the sugar dissolved in water. So when you say sugar solution, you don't say water solution or something like that. Sugar is the exciting part. And that's what I like to think of informally as the definition of a solute. It's the exciting part. So when we're breathing, we think about the air to breathe, not the nitrogen. Air would be the solute and solvent would be nitrogen. In the sugar solution, water is the solvent and sugar would be the solute. But that's my own personal version. You should probably consider the official definitions. Ionic molecules not only dissolve in water, but they also dissociate. And I want to kind of remind you of that. So sodium chloride is a solid just like sugar. And when it goes into water, it dissolves. The solid goes away. You've got one phase. So initially, you'd think you might write NaClAq, which would be sodium chloride dissolved in water. But remember, and this will be important in this chapter, the ionic compounds in water break up into the cations and anions. So sodium chloride is actually Na plus ions floating around in the water and chloride ions floating around in the water. And this will be important to us later on. So just hang tight on that memory. Another thing that's good to remember is the idea of soluble and insoluble. And soluble is when one substance dissolves in another, all right? So the salt water solution, the NaClAq, which breaks into Na plus and Cl minus ions in water, that would be an example of compounds which are soluble. They mix really well together. But there are also combinations of chemicals that are insoluble. They don't mix very well. So for example, oil and water don't mix. Maybe you've heard that expression before. That just means you put oil and water in it. Usually oil floats on the top of the water. It's less dense, all that kind of stuff, but they don't mix very well. So solubility has a big time importance with intermolecular forces that we talked about in the last chapter, and we'll consider that as we go through this section. Chemists a lot of times use the idea like dissolves like to figure out, at least on a rough basis, when things dissolve or not, when they're soluble or not. And the closer the intermolecular forces are to each other, the more likely they are to dissolve. So if you have to guess if two substances will be soluble, if they'll dissolve, or if they're insoluble, they won't dissolve, a really good rule of thumb is to have similar intermolecular forces will dissolve some other similar intermolecular forces. So what I mean by that, polar substances generally dissolve in polar solvents, and nonpolar substances generally dissolve in nonpolar solvents. It's rare for polar substances and nonpolar substances to get along, if you will. That would be an insoluble example. So for example of that, water dissolves really well in ethanol. Ethanol is drinking alcohol, by the way. Just say no, kids. Anyway, ethanol has a polar hydrogen bond to it. It has an OH bond on it. So it gets along really well with water, which has lots of OH bonds. Oil dissolves really well in kerosene. All right. Oil and kerosene are both basically non-polar combinations of molecules. And so they get along really well. However, oil and water don't get along very well at all because oil is almost exclusively induced dipole, the ID you see right there, which means it's non-polar. Water, on the other hand, is incredibly polar with hydrogen bonds. It doesn't usually get along real well with oil. Now, small amounts of oil will dissolve in water. It's true. And this is a problem with pollution. And sometimes people worry about how the water smells because of dissolved substances. But it's a very small amount. And so in general, like dissolves like works really well for chemists. But you should always confirm this with data, stuff like that. So here's a question you might see. It says, which of the following solvents would you expect lithium chloride to be highly soluble? And you can see there's water, carbon tetrachloride, carbon disulfide is C, D, that compound is butane, liquid butane, and E is a compound called benzene. You don't have to worry about any of that. But what I would like you to think about are the types of intermolecular forces happening. So lithium chloride is ionic. It's got a positive Li and a Cl minus, and those are going to be pretty strong forces. And water, as you know, is basically the answer to everything in these classes. But anyway, water, let's not be kind of silly about it. Water has extensive hydrogen bonding, so it's not just dipole, it's extreme hydrogen bonding, if you will. And ion dipole forces form when ions like lithium plus and chloride minus interact with something very polar like water. So big surprise, it's going to be water. Lithium chloride is ionic. Water is polar with hydrogen bonds. So when they come together, it's easy to make the ion dipole force, which is pretty strong. The other compounds down there are essentially nonpolar. So they would use induced dipole forces, which are much weaker, of course, than the ion forces and the hydrogen bonding forces. To further your knowledge of this area, here are some examples. Let's say that I asked you, is vitamin C water soluble? All right. And here's the structure for vitamin C. Now, you don't have to know what all these groups mean stuff, but what I hope you're seeing is that vitamin C has a lot of OH groups on it. And every time you have an OH, that's going to be a site of hydrogen bonding. And water is really into hydrogen bonding, like we've said already. So we would say absolutely. Those 4 OH groups are going to love water because water has OH groups. So vitamin C is a water-soluble vitamin. Here's the structure for vitamin K3. And the question is this one water soluble? And if you look at this structure, which has a lot of kind of cool organic chemistry things that we'll talk about next quarter a little bit. Anyway, vitamin K3 doesn't have any OH bonds or any NH bonds or FH for that matter, although that's not very likely. But anyway, there aren't any of the types of bonds that water would like to make intermolecular force interactions with. Everything on there looks like it's probably a little bit polar, but there's a lot of carbons and hydrogens, and if everything's the same, there's not going to be a lot of polarity. So I would predict that vitamin K3 was not water soluble. This is mostly a non-polar molecule. The carbon-oxygen double bonds do create a little bit of polarity in the molecule, and there's some other asymmetric ingredients for this molecule. But overall, I don't think there's enough polarity to make make this soluble in water. So I would predict this to not be water soluble. And if you look this up in the list of vitamins, vitamin K3 is considered fat soluble. Fats are essentially nonpolar. Nonpolar things get along well with nonpolar things. That's going to be how people classify these. So it all comes down to intermolecular forces once again. That's why they're so important to chemists. Now, electrolytes are important concepts, and I talked about them briefly, but I want to hit this again. If you have a covalent molecule that dissolves in water, like sugar, which I showed you earlier, no problem. Sugar dissolves really well. You put some sugar in water, you dissolve it up. The sugar, the solid sugar, goes away, quote unquote, but if you taste it, you can totally taste the water in the water solution. So covalent molecules dissolve. They are hydrated. The waters go around them, which is no problem. But ionic compounds are different. Ionic compounds not only dissolve if they're soluble, but they also dissociate into the cations and anions. So sodium chloride, as I stated earlier, doesn't just, you wouldn't just write NaClAq, you would write Na plus AQ and Cl minus AQ. They not only dissolve, but they dissociate into the ions, and that will be important coming up here. If you have a dissociated ionic species, and you have these positive and negative ions running around, you can actually conduct electricity through them, which is amazing. So on the upper right-hand side there, I've got 3 examples of different types of solutions, all right? And I want you to focus mostly on the left and the far right. On the far left, it says there's no ions. If you have something covalent, like sugar, and it goes into water, it dissolves really well, but you don't have positives and negatives. And electricity is essentially a series of negative electrons, and negative electrons need positive things to kind of conduct through. So if you don't have any positives and negatives, you won't have any electricity. Covalent molecules are usually considered to be non-electrolytes. That means you don't have any ions. The electrons can't transfer from one side of the solution to the other. No electricity is going to be conducted. And we're going to put in Chem 222 that all covalent molecules do not conduct electricity. So if a covalent molecule dissolves in water, it's considered a non-electrolyte. On the other hand, on the far right, what happens with a lot of ionic compounds is they dissociate almost 100%. Sodium chloride, potassium nitrate, even hydrochloric acid will do this. Strong electrolytes are what usually happens when you place ionic compounds in water. You end up with lots and lots of ions. And if you have lots of ions, the electrons can flow freely and you have conductivity of electrons. Strong electrolytes. So notice in those pictures on the far left there, there's no light in the light bulb when it's the non-electrolyte, like covalent bonds, because no electrons can go through. On the other hand, on the far right, you can see that light bulb is very, very bright, all right? Electrons flowing through it, no problem. Now, there are also examples, and this will be important to us more probably in Chem 223 than Chem 222, but there are compounds that are ionic, but they don't dissociate 100%. And if you have one of these, it's called a weak electrolyte. And if you remember from our acid and base discussion in Chem 221, you can have weak acids and weak bases. Weak acids and weak bases don't break up 100% into positive and negative cations and anions. So they're considered weak electrolytes. And as an example of this, acetic acid and ammonia are both weak systems. Acetic acid is a weak acid, ammonia is a weak base. And both of those, roughly every 10,000 molecules, one of them will dissociate. So in acetic acid, you'd make an H plus and the acetate ion. Ammonia, on the other hand, will react with water to make ammonium and hydroxide. However, it's only 1 in 10,000 of those that will actually break into positives and negatives. Most of them stay the same. So we'll talk more about weak electrolytes, but for right now, just notice that that light bulb up there, not very bright. You don't have as many ions. The electrons don't conduct as well from one side of the solution to the other. That's where the idea of the weak electrolyte pops in. Okay, so here's a question you might see. It said, how would you classify magnesium nitrate dissolved in water? And you can see there's non-electrolyte, weak electrolyte, strong electrolyte, Gatorade, or more information is needed. Well, first of all, it's not Gatorade. I'll let you know that. And you can absolutely answer this. So magnesium nitrate has a positive magnesium. Nitrate is NO3 minus 1, which is a polyatomic ion, and it dissolves all the time. There were no exceptions for nitrate being insoluble, if you remember from the solubility table. So magnesium and nitrate will break up 100% into magnesium 2+ ions and nitrate ions. And when an ionic compound dissociates and dissolves, like this one will, it's going to be a strong electrolyte. All right, that magnesium nitrate will not stay together. It's going to break up into magnesium 2+ and 2 nitrate ions. We're going to get 3 ions out for every magnesium nitrate that goes in, and 3 to 1 is going to create a lot of ions. That thing is going to light up like a Christmas tree. So yep, it's going to be a strong electrolyte.
A strong electrolyte is a compound that ionizes completely in solution. Hydrogen chloride breaks into hydrogen and chlorine ions.
So as a quick review from Chemistry 221, we talked about strong acids, strong bases, weak acids, and weak bases. And why that's relevant now is that all those strong acids will dissociate 100% into cations and anions. So if you have a strong acid or a strong base, they're going to be strong electrolytes. Also, all of the compounds that dissolve, that are soluble, all right, and according to our solubility guide there in the upper right, all of those are going to be strong electrolytes. So you can see up there in the right hand corner, the soluble ions always will have usually sodium, potassium, ammonium, nitrate, perchlorate, things like that. We also talked about how chloride, bromide, and iodide are usually soluble except for with silver, mercury, lead, stuff like that. Anything that's soluble, you put AQ next to, and those will break up 100% into cations and anions. So there's a lot of strong electrolytes out there. All the strong acids, all the strong bases, and all the ionic compounds that dissolve in water. So again, those 5 strong acids and 3 strong bases, pretty important for lots of reasons. Here's another reason: they're going to be strong electrolytes. Now, all of the weak acids and weak bases, though, those are going to be weak electrolytes. And if something is insoluble, so for example, if you have barium carbonate, for example, barium carbonate has a carbonate, and most of the time carbonates are insoluble unless they're with ammonium or the alkali metals, which is rare. That's going to be an example of an insoluble compound. That's not going to conduct electricity. It has to dissolve first. Barium carbonate doesn't even dissolve in water, at least according to what we've learned so far.
A weak electrolyte is a compound that only partially ionizes in solution. Some hydrogen ions dissociate from acetic acid molecules, but others may rebond at the same time. Some compounds that dissolve in water, such as ethanol, do not dissociate into ions at all. Such compounds are called non-electrolytes.
Okay, a lot of information in those 2 videos, so let's break this down. So what's really important here is that we have strong electrolytes, weak electrolytes, and non-electrolytes. And the strong electrolytes, which we talked about in the previous page, are basically strong acids, strong bases, and ionic compounds that dissolve well in water. And you can use the solubility guide to do that. Now, weak electrolytes are basically going to be weak acids and weak bases. And on the right-hand side there are several examples of both weak acids and weak bases. If you see an acid or a base and it's not one of the strong acids and strong bases, you can definitely assume in this class that it's going to be a weak acid or a weak base. And that means it's going to be a weak electrolyte. So as an example of that, if you had, say, 10,000 molecules of ethylamine down there, which is a strange base, but anyway, 10,000 molecules of that, you would have 1 in 10,000 of the ethylamines react with water. It would make some hydrogen hydroxide, and you'd have some kind of weird other conjugate species, which we'll talk about in Chem 223, but only 1 in 10,000 of those do that. So it's considered a weak electrolyte. It doesn't conduct electricity very well, and all the weak acids and weak bases will do that. And then finally, there are non-electrolytes. Those would be the sugar solutions and my beloved coffee. And if you have ethanol, drinking alcohol, and water, stuff like that, those are all covalent molecules that dissolve in water. And water's pretty good about doing some of them, like vitamin C, for example. All of those are non-electrolytes because you don't have positives and negatives running around. And if you don't have positives and negatives, you can't have electricity go through, and there's no light in the light bulb. And that will be important for us coming up here.